Krzysztof will talk about untangent con to system of inequalities and equation in Banach spaces on the relaxed constant rank condition. Please, it's with you, Krzysztof.
Okay, thank you for introduction. First, I would like to thank the organizers for giving me opportunity to give this talk. This presentation is based on joint work with Ewa Bednarczuk and Krzysztof Leśniewski. And as you will see in a moment, the beginning of the presentation is almost the same as it was during my presentation 1 year ago. So one more time, I will be trying to connect relaxed constant rank condition with Abadie condition. During my previous presentation, our domain space was a Banach space, and we was dealing only with a finite number of constraints. So today, I think we have a much better result because we will be dealing with infinite number of constraints, infinite number of functions. So one more time, the beginning is the same, but in a moment you will see a much better result. So we are dealing with the following problem. We want to minimize function f, and our domain set is called capital F. We have some inclusion defining this set. G of x is in K. And we are interested on some regularity condition which implies non-emptiness of the set of Lagrange multipliers. So one more time, I'm interested in Abadie condition. So here you can see the definition of tangent con and linearized one, and we are saying that Abadie condition holds if these two cons are equal. So we are looking for some regularity conditions implying that that these two cons are the same. So in the above paper, you can see a very nice proposition. So if x0 is a local minimizer and Abadie condition holds, then we are getting non-emptiness of the set of Lagrange multipliers. So here, let me also underline the fact that they are using infinite settings. So domain space and value space are maybe infinite. But they are assuming that M of x00 is weakly star closed. So this set so in the definition of Abadie condition, they are assuming that these two cons must be equal, and this set M of x00 is weak star closed. And then with Abadie condition, we are getting non-emptiness of the set of Lagrange multipliers. Sorry for that. Okay. So for infinite settings, there are only few regularity conditions. And for example, in this paper, you can see some connections. So for example, there is no equivalence between con point property and Abadie condition. And what about finite dimensional settings? So here our domain set is Rn, and on this slide we are dealing only with a finite number of functions. So for such settings there are plenty of regularity conditions, and maybe let me focus only on 3 of them. So the first one is Mangasarian-Fromowicz. We are saying that such condition holds for f if gradients are linearly independent and there is some z satisfying these two conditions. Next regularity condition is strictly connected with our main tool, which is constant rank. So we are saying that constant rank holds at x0 for our set f is if these two ranks are the same. So here we are switching this argument of gradients. And next one, relaxed constant rank condition. So here we are assuming that constant rank holds for each index set j satisfying the following two inclusions. So one more time, these two numbers must be the same. So what about some connections between these conditions? So in the paper of Kruger, Minchenko, Utrata, you can find, for example, such graph. So you can see that relax Mangasarian Fromowitz and, for example, relax constant rank implies Abadie condition. So we want to generalize such fact for infinite dimensional settings. So what about our assumptions? So we are assuming that E is a Banach space and F is a Hilbert space with some Schauder basis. So if we have Schauder basis Bi, then we are also getting associated functionals Bi star. And we have the following property, Bi star of Bj is equal to 0 and 1 only if I is equal to j. So using this Schauder base, I can define the following con. So here, for example, for some indexes, coefficients are equal to 0, and for some others, these coefficients are less than equal than 0. So let me underline the fact here that both of these indexes may be infinite. We are assuming only that this sum is equal to the set of natural numbers. And what about some properties of such cons? So we are getting that there are no interior points. The idea of using such cons is from Fullerton, and you can find some properties of such cons in MacArthur papers. So now we want to rewrite our set F using this con, and one more time, what I want to get is the following implication. So from relax constant rank condition, I want to imply Abadie condition. So just using definition of con K, we can rewrite our set F like this. And one more time, so maybe let me go back for a moment. Sorry for that. So, okay, so one more time, our set F is given by the following formula. And what about some examples? So example 1 is the same as it was during the previous presentation. So we have finite number of functions, but looking into example 2, for example, taking F equal to L2 and canonical base, we can now deal with problems with infinite number of constraints. So what I want to underline here is the fact that not all of natural cons may be represented in the following way. So for example, in our paper, you can find such examples. So for capital L2 plus may not be represented in the following way. So there is no Schauder base such that we have the following equality. And what about our main tools? So here you can see 3 important theorems for us. A rank theorem, a local representation theorem, and Ljusternik theorem. So in rank theorem, what I want to underline is that our derivative splits and the following mapping is an isomorphism. And if that's the case, then there are some subsets and some diffeomorphisms such that we are getting the following equality. In local representation theorem, what I want to underline is that we need to this split be in special form. So E2 must be equal to kernel. And then we are getting the following diffeomorphism. So at the top, I'm assuming that F is C1 class. So here R is equal to 1, but assuming that F is CR class, here we are getting CR diffeomorphism. And next one is Ljusternik. So if image of our derivative is equal to y, considering the following set, we are getting that tangent space to this set is equal to kernel of derivative of this operator. So how to formulate a constant rank condition for such settings where we have infinite number of functions? So here you can see our definition. We say that CRC holds for Fi, so I1 may be finite or infinite set if there is some subset J2 such that this sequence forms a basis for the following subspace. And furthermore, we are assuming that there exists isomorphism Z of X. And one more thing, this isomorphism is of special form. We need the following equality. So what about the connection between finite settings? These two definitions coincide. And let me recall that if we have, for example, Vi and Wi in some Banach space or Hilbert space, then these two basic sequences are equivalent if for all sequences this series converges, if and only if this series is convergent in our space. So one more time, we can look into CRC definition, and we can say that these two basic sequences are equivalent. So here we are switching argument from x to x0. So these two sequences must be equivalent, basic sequences. Some more properties of Schauder basis. So we are saying that Vn is boundedly complete if such supremum is finite, then such series converges. And we have a very nice theorem from James. X is reflexive if Banach, if X is Banach space, and it is reflexive if basis of this space is both boundedly complete and shrinking. And what shrinking means? It means that associated functionals forms the basis for a dual space. And two other properties. If we have basis Ci, we are saying that it is Besselian if we have the following implication. And the second property is strictly connected with the property with Hilbert spaces. So Hilbertian, if this series converges, this is the series of real numbers, then this element, this is converges to the element of our space. So even in Hilbert spaces, there are bases which are not Besselian and not Hilbertian. And if we have these two conditions, so if Ci satisfy both of these two conditions, then this basis is equivalent to canonical basis of L2. So using these properties of Banach basis, we can formulate the following proposition. So here we are dealing with some C1 mapping. We are assuming that E2 is a kernel of derivative, and we are defining the following subspace. If our sequence, the Fi, forms shrinking and boundedly complete basis for X1, and this sequence is Besselian, and here dual associated functionals are elements of E. So here we are not assuming that E is reflexive. So we need this third assumption. Then we have the following split. And moreover, if we assume CRC with some index set J2, then we are getting that the following mapping is an isomorphism. So let me go back to our main tools. Okay, so sorry for that, it's not working well. Here are our main tools. So one more time, we need such mapping to be an isomorphism, and we need the following split. Okay, so sorry for that. Okay. So next proposition: if E is a Banach space and we have the following mapping, C1 mapping, E2 is a kernel of our operator and the previous conditions are satisfied, then we are getting some kind of implicit function theorem. So we can express other coefficients of our vector using this composition. So how to define a relaxed constant rank condition? In the same way it was for constant rank. So here you can see one more time a definition of our domain set. And we are saying that RC/RCQ holds for F if there exists some neighborhood such that for all indexes J satisfying the following two inclusions, CRC holds for such sequence. So here you can see one more time the definition of CRC. Okay, so next assumption, unfortunately, we was not able to prove our main theorem without another assumption, which is called H1. So for each vectors from linearized cone, we are looking for some number epsilon 0 such that this inequality holds for such indexes. And for example, in the paper of Morduchowicz and Dia, you can see a different assumption. It is called perturbed Mangasarian-Fromowicz condition. And in our paper, you can see an example where perturbed Mangasarian-Fromowicz condition is not satisfied. Our assumption is satisfied, and we are getting equality between these two cones. So Abadie condition holds. So now let me show you our main result. So one more time, E is a Banach space, F is a Hilbert space with Besselian Schauder base. We are assuming that RC/RCQ holds for F, and our assumption H1. Then we are getting Abadie condition. So now I want to present you the idea of the proof. So one inclusion is obvious. So let us start with taking D from linearized cone, and we are defining the following set M. So from Ljusternik theorem, we are getting that tangent space to this set M must be equal to kernel. So we are trying to calculate kernel of our derivative. So we are getting two cases. J2 is equal to J, then just using Ljusternik theorem, we are getting that D must be in the following set. And in case 2, where J2 is not equal to J, then using our proposition 2 and our implicit function theorem, one more time calculating kernel of our derivative, we are getting that D must be in this set. And now using assumption H1, we can prove that D is also an element of tangent cone. So we are proving Abadie condition. Okay, so a little bit about Lagrange multipliers. So I was saying that if M of x 0, 0 is weakly star closed, then we are getting non-emptiness of the set of Lagrange multipliers. And now with our settings, we can present you the following proposition. So here we are looking into the same assumption as it was in our main theorem. And additionally, if M of x0, 0 is weakly closed, then we are getting that the following set is non-empty. So that's all, and thank you for your attention.
Thank you very much, Krzysztof. Questions? There are some questions. We have time for some questions. Okay, I will make a quick question. Do you show an example in which the Abadie condition is satisfied and the condition shown by Mordkovich and Nia is not? Did you prove that that's always happen? I mean, always that the Mordkovich and Nia's condition is satisfied, Abadie is satisfied as well?
So this is just an example. So for example, if x is L2, of course, these coefficients AI, BI, and CI must be of special form because series mass convergence. But we are getting that even taking arbitrary CI like this, Mordkovich condition is not satisfied. Because using Mordkovich condition, we are getting that this number of functions must be finite.
Yep.
And in our case, assumption H1 is satisfied, and even for infinite number of functions. So this is why I was thinking this example is interesting, because still infinite number of constraints and everything works well.
That's good. Very good. Thank you. Questions? Any more questions?
Let me ask, have you some applications in, say, calculus operations or optimal control of your results? Are there any perspectives to have such applications?
Not yet. I was just looking into generalization of well-known facts. But I'm looking for some applications, of course.
Very good.
It was just a natural question. Is it possible to get some regularity condition when we have infinite number of functions? Yes, that was just a mathematical question.
Yes, yes, of course. Thank you.
I also have a question.
Yes, please.
Do you have an example available where your RCPLD holds or your constant rank assumption holds, but the weak star closedness of the set MX00 is not valid?
No, not yet. Not yet.
Yeah, that would be interesting, whether your very special setting implies this weak star closedness actually.
Yes, yes, it is interesting. And of course, we need to consider an example with domain in some Banach space, not a finite dimension. So this is why it is some kind tricky, because for now I was writing only very simple examples when domain space is R or Rn. So asking to your question is some kind tricky, because I need to think about much more complicated example.
Yeah, of course. That's the problem with Abadie in Banach spaces, yeah, because you need this weak star closedness, and that does not come for free. And yeah, that's that's the essential problem there.
Yes.
More questions? Krzysztof, let me ask you a quick question. It's not relative with Abadie assumption. It's about that class of equivalence between sequence. There is often techniques to identify when two sequences are equivalent.
Yes, there are some. You don't need to find an isomorphism such that image of particular vector is with the same indexes, but there are some propositions. For example, in Albiach book, you can find some characterizations.
Good.
And for example, for Hilbert spaces, we are getting some connections between Besselian and Hilbertian, and then we are getting equivalence with L2. And for C0 space, which is not Hilbert, there are some other propositions, and so on and so on.
Ah, that's good. Very good. Thank you. More question, guys?
Let me say a remark. There is much more stronger variant of Ljusternik theorem. Maybe it will help you in future studies. If you say you have operator G and the point x0, and you have this condition that G prime of x0, x is equal to y, that is surjectivity. Then there is for every point x in the neighborhood of x0, you have the following estimate to the level G of x equal to 0. It's simply the norm of G of x. This is very important, stronger result than Ljusternik theorem.
Okay, so no, so I will write an email to you.
Okay, let's discuss. Thank you.
With question about some references, and yeah. I will think about it.
Of course, I will write you. Okay, I will write.
Okay, guys. If there is no more question, please join me to thanks again, Krzysztof.
Thank you.
Thank you. Thank you, Krzysztof. If you can stop sharing.
Yes, in a moment.
Yeah, no worries.
Wait, is because I'm using two monitors, and unfortunately. Oh, okay.
That's okay. Thank you very much.